Okay. All right, so here we have a circular table which could be drawn better, but it's okay. And it's rotating at 240 RPM. And from the center of the table, there's a spring attached to a mass. And I drew these little lines in because the mass can only move radially with respect to the circular table. The spring constant is given by K. The mass is given by M. Or M. Okay. It can only move radially. The spring constant's K, and the length of the spring is L. So our spring force is minus K, and it wants us to find a relation between the mass and the length d to which the spring stretches while the table is rotating. So our force will be d minus L, where d is whatever length it reaches and L is its equilibrium length. So our force, and it's negative as it's a restoring force, so a force to bring it back. Now as the table rotates, we're going to get a centripetal force, which must be equal to minus m r, or using omega is v r. Yeah, omega is v over r, sorry. Omega is v over r. And solving for v, we can plug that in here and get minus m omega squared r. So our restoring force here, which is our spring force, must be equal to our centripetal force, or minus K d minus L is equal to minus m omega squared r. Canceling signs. Now the r here is the radius at which the mass is rotating, which we're given in the problem is just d. So we can put that in. K d minus L is equal to m omega squared d. And it wants us to find a relation between the mass m and the length d to which the spring, I assume the length d in terms of the other terms. So we have K d minus KL is equal to m omega squared d. We can now bring some terms over, so K d minus m omega squared d is KL. Might as well pull d out of here and say K minus m omega squared is equal to KL, or our distance is KL over K minus m omega squared. And we can pull the k's out and write it as L over 1 minus m omega squared over K, like that. And I guess we could clean this, or we could add some numerical values, although I'm not sure what the point is since we're not given any of the other ones. But omega is 240 RPM, which is 240 times 2 pi times 1 minute per second, per 60 seconds. To put it into radians per second, or per seconds, so then our omega squared would be 631.65 per second squared. And so we could then write our d as L over 1 minus m 631.65 per second squared over k. So then that would be the length d to which the spring stretches while the table is rotating in terms of its equilibrium length, the force constant on the spring, and its mass. Okay, so checking here. So our force is given by just kd, which I wouldn't say is quite true, because unless the equilibrium length is purely purely due to d, or if you set the 0 at L, I suppose, but that's not a good idea. But then your R comes out to be L plus D. Now that I think that will give you some trouble due to just moving your origin from the spring to the center of the table. Yeah, I think that would give you some trouble. But it might be solvable that way. Yeah, it should be solvable that way, actually. But then here, I wouldn't say this gives you the relation between the mass and the length d, purely because d is on both sides of the equation, so it's incomplete. So I'd say it's incomplete. D is on both sides of the equation. Not solved fully. But would it give you the same thing? Yeah, I think it would actually. Yeah, it looks like it, because you divide by these. I think so. But it's incomplete because it's not solved for D. I'm just going to say it's incorrect.